Okay, so we finished last class on direct map caches, and we looked at why conflict misses are common with direct map caches and how they can be pathologic. So the solution to this is to go to something that we call set associative caches. And the idea is that rather than each set storing a single block, you allow that set to store multiple ones. And then you can choose which block to store your data in. Okay? And this will reduce conflict misses because now there are multiple options. So if you go 0, 8, 0, 8, 0, 8, like we had in the previous lecture, you can put both 0 and 8 into that set. And then when you go back and forth, you'll hit every time. Okay. So when you have a cache that has really high associativity, this can lead you to much fewer cache conflicts. But it turns out they increase the hardware cost of your cache significantly. So here's an example of a two-way set associative cache. And the book uses E-way, and then where E is equal to 2. So in this case, this is the picture of it. So each set, which is the horizontal blue box, each set has 2 entries that it supports. And to take an address and to look up whether or not it has data in this particular cache, for a particular block size, say this block size is 8 bytes per block, you would use the least significant 3 bits to identify which byte in this block you want to return. Then you would use the next significant bits as the set index. And this will choose which one of these sets that you will look for your data in. And so when you find this set, then what you're going to do is you're going to look at both locations for your data at the same time. So that's what you do. You select this row, and then what you do is you need to see if your data, based on the tag bits that are associated with your address, if your data is either in this block or in this block. So you compare both simultaneously. And then if the tag matches, which it does here, and the valid bit is 1, meaning that that was something that you had placed there before, it's not just garbage previously encoded data, then you use the block offset to figure out which byte in this block to return. And in this case, you're accessing the 4th block, or the 4th byte, and then you return the 2 bytes that are there. So I think I said that we were accessing a short in this example. Yep.
Doesn't that mean that each memory, each core, right, has to have its own set of cache for it? So that way,
yes.
Like, yeah, because you can't have a bunch of stuff like interactants.
Yes. So
if you're taking both.
Typically, we'll get to how caches are assigned cores. Sometimes caches are unified across all cores. Sometimes they're specific to a single one. Yes. Okay. So one of the things that happens is that if there is no match, then if you decide to bring in that line from memory, now you have a choice. You can either replace the one on the left or the one on the right if they both missed. And so that choice of replacement is configurable for a cache. You could say least frequently used, least recently used. You could do random. That's a replacement policy that we'll talk about later. Okay. One of the big drawbacks about set associative cache is this parallel compare. So now here is your cache. It's got it's a two-way set associative cache. Now, in order to do this parallel comparison of the address that you're putting in, you need to basically add identical comparator circuits against the tag fields of both sides of both sets. And then you would have some, and that's what this is. This is the equality circuit. So for you EE folks, that might make sense, but that's basically what this is. And then you're going to check to see whether or not you hit or miss by seeing whether or not these things are equal. And so this is the circuitry. And then I'm only showing it to you because these are gates in hardware that cost you money. So that's the implementation cost. Okay, so let's go back to our original example, and we're going to simulate a two-way set associative cache, and we're going to use this 16-byte main memory. And so there's 4 bits for the address. It's going to be the block size is 2 bytes. So each one of these blocks has 2 bytes in it. The number of bits that are required to identify which byte you're interested in is 1. So log base 2 of 2 is 1. And because you have 2 sets, the number of set bits that you would need is also 1. So then we have this address stream, 01780. And so the underlined digit is your set ID. And then the right-hand side is the block offset. And then the left part is your tag. So let's go through this cache simulation. Everything misses at the beginning. What you bring in, and try and simulate this ahead of time as I walk through here, you bring in a block with set 0, with tag 00, and the data that you're going to bring back is 0011. So that's your first data that gets back. When you go and access 0001, you can compare this. You go to the set 0. You look for the tag 00. It matches. Then you can go to the block offset of 1, and you can hit with hex 11 being returned. 0111 will go to set number 1. We'll set the tag to 01, and we'll bring in the block, the bytes 0110 and 0111, because those are the addresses that match that particular pattern. So this is a miss, followed by bringing in the 0110 and the 0111 bytes. Is that clear? Yeah.
How do you determine which set it's going to go to?
Because of this underlined bit. It's using that to sort out which bytes go to set 0 and which bytes go to set 1.
Which one goes? So that's technically two caches essentially that it has access to.
Well, it's one cache, but it's got distinct sets, and so typically your main memory will map itself into one set, just for ease of implementation. Because if this was just one shared set, then you're basically going to have to search every single line when you have an address. So we started out with the direct map cache, where you partition the cache into a huge number of sets, the most. And then we saw that the conflict misses happened, so now we're going to reduce the number of sets, and then we're going to allow multiple lines per set. That's going to cost us in hardware, but then now when I identify the set, there's multiple options in that set. And just like before, we're using the set bits, we're using parts of the address to identify which set we're going to look for, or we're going to look for our data in. So that's a miss. The next one, 1000, the set that you look for is set 0. The tag is 10, so this misses. And then you bring that block in, and so you bring in 1000 and 1001, so that's byte 88 and 99. And then when you access address 0 again, because you didn't have to replace this block with this access, you now have a hit. Whereas before, with the direct map cache, when there was only one entry, you were thrashing. You were going back and forth between 0 and 8. Okay, so here's a practice problem. There's some scrap paper here. Now that we know how to use the bits of the address to index into the cache, I want you to do this problem. We have an 8-block cache, and in this 8-byte cache, each of these blocks is 16 bytes. And we're going to organize these blocks in different ways. We're going to have a direct map cache, which is here, a 2-way set associative cache, which is over here on the right, and a 4-way set associative cache, which is at the bottom, I want you to use the address bits to color in the line that this particular address up here will belong to. Color in the set in each one of these three caches. And so to make it, to start you off, because the block size is 16 bytes, you know that the last 4 significant bits of the address are used for the block offset. And then the set bits start immediately after that. So then it becomes that how many bits do I need to index this direct map cache set size? How many bits for that one and how many bits for this one? And that will determine which set number this belongs to. So I'll give you a minute for this. Yeah, so how many bits would you need to index this? 3 bits, right? So it's log base 2 of 8. So you need 000, 001, all the way to 111.
Isn't that for the tag though?
This is for the set index. The tag is everything else. That uniquely identifies your data as being yours. You need the rest of the bits.
So you're gonna have 4 bytes for the block.
4 bits for the
4 bits.
Yep.
3 for the set for that one at least, and the rest are gonna be tags.
Yep. And so then, which one? So do the first one. Which set would that address belong to here? Set number 3, right? So, and the way you get that is, actually, do I have it? I do have it. So you take the next 3 bits as your set because you need 3 bits to index this. And so the next 3 bits are 0, 1, 1. That is 3. So that's why it's set number 3 is where this belongs. So for the two-way cache, it's also set 3, because if you take away this bit, it's still 3. You take the 2 bits, and that specifies set number 3. So yeah, there's only 4 sets, so you only take 2 bits out of it. And then the rest is the tag. So here, the dark blue is the tag, and it's 6 bits of tag. Here it's 7 bits of tag because you've used associativity for it. And then the final one is 1, because you only need a single bit to determine the set, and then the rest of this is the tag. Other questions on this?
With the block is indexed into, it's just you do a simultaneous compare.
You do a simultaneous. So yeah, then the next thing is you simultaneously compare on all 4 of these blocks to see which one has this tag match. And the one that does, then you can index into the 3rd byte of the block. Let's say it's this one. You go into the 3rd byte. There's 16 bytes here. You go into the 3rd byte, return that. That's the rest of the cache operation. The last 4 bits. The light blue bits are the block offset bits. Yeah, on this figure.
So the ones just above that, right?
Which ones?
The ones you have in green over there? Is that one?
These are the set bits. So right above the block offset bits are your set bits to determine which set you're going to look at.
If it was a short in that last example where we're taking the 3rd byte, it would take the 3rd and the 2nd byte, right?
Yeah, yeah. Well, hopefully when you access the short, it's aligned.
Right.
And then it would have given you, hopefully your short was at 0010, and then you would return 0010 to 11, the 2nd and the 3rd. Okay, practice problem 612. Consider a two-way set associative cache. It has 8 sets, so 2 blocks per set, and then 4 bytes per block. First, find the capacity of this cache using the formula that we see if you can remember the formula from last class. It's given these parameters. It's pretty straightforward. Draw a figure of this cache, similar to what we had earlier. like this, draw a figure like this, and then draw a diagram of which parts of the address are used for the block offset, the set index, and the cache tag, basically. So recreating this figure up here is what this question is asking you to do. So just to give you practice. Better cache? All right, so S times E times B is the capacity of your cache, 64 bytes. A figure, basically you have a two-way, let me not use the pointer. So each set has 2 lines in it. Each line or each block has 4 bytes in it. So data 0 to data 3 is how I'm labeling it. And then you have 8 sets. So this goes from 0 to 7. So in terms of the diagram, how many bits for the block offset? 2. You need 2 bits to get 4 locations. How many for the set index? 3, because you have 8 sets, and then the rest is the tag. So that's basically what you're doing. 2 bits for the block offset, 3 bits for the set. The other 8 bits are your tag. Given this, these are the questions that you might get on an exam. So I have this cache, this identical cache that you had in the previous practice problem. What is the block offset of this address in hexadecimal, the set index, and the cache tag? Does this access hit or miss in the cache, and what is the value that's returned if it's a hit? So this is, the way you're going to solve this is to take this hex address and blow it up in bits. Expand it out, and then reorganize the bits based on this layout that you just told me was the way to access this set, this cache. Yes? So now, actually, they have, this is an alpha version of the website. So if you go to Oregon CTF :8000, Chapter 3, Chapter 5, and Chapter 6 problems are now there. So yeah, and there's several of these over there. So for practice, I definitely recommend that. There might be an update over the weekend, so we're trying to debug iron out the questions, but definitely by the time your final rolls around, I would definitely recommend going through all those practice problems on that site, and that'll give you at least a representative set of what's going to be on an exam. All right, so I'll give you some time for this. Okay, so the first thing you do is you blow up the bits. So I might as well do this. So this turns into 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. And then if you look, the least significant 2 bits is the block offset. So 0x0. Oh, actually, that's going to fill. Yeah, that's going to fill in. Set index is the next 3 bits. So 101. So the set index is 5. The cache tag is the rest. So this is 0001, and then this is 0111. So the cache tag is hex 71. The set is hex 5. Block offset is 0. Does it hit or miss? So if I go into the cache, and one of the things that I have here is that if the cache line is blank, the cache line is blank, then it's an invalid line. So for this, you go to set 5, you look for cache tag 71, and there's 71 right there, and you go for a block offset of 0, 0. So that actually, in this figure, the 0 is on this side. So it's 0B. So 0, 5, 71 hit, and hex 0B. Yeah.
So shouldn't, for like something like a 13-bit M, shouldn't we actually, and this sort of setup, wouldn't our tag actually have to be three digits because we were missing those first three?
Yeah, I mean,
Okay.
I got rid of the leading digit.
Well, because
The
like
zero.
I mean, it greatly changes the way that you do your count. Like that's because like I guess in this case it's not because we started out with a 0. But
For ease.
You got 16 bits in that address. Is that
Yeah, I mean, that extra bit has to be encoded somehow, so we encode it as a hex digit. Yeah. Yeah, it would be nicer if it was a power of 2, then I wouldn't have to answer these questions. But yeah, it's not my practice problem, so it's 13. So yeah, but that's correct.
I'm not insane.
All right, more practice. Here's another address. Repeat.
Yeah, I might need another.
Oh, really?
I guess that's not a problem.
All right, so I'm not going to walk through, go through this step by step. Whoa, I didn't want to go that fast. How's it look? Somewhere close?
Oh, 6E.
So, would you like me to walk through it, or is this close to what you got?
I think I must have converted my binary wrong. D.
So when it's a miss, it just.
D is 1101. So yeah, 1101, 1101, 0101. And then you regroup those and you should. And then this is invalid because 6E, when you go to set 5, 6E is blank. So yeah.
Are we going to be converting hex to binary or text?
Yes, for sure. Guaranteed. That one I can guarantee. Without a calculator too. So that's I think that's a bare minimum of math computation that I could expect you guys to have out of here. So, yes. Here's another form of the question that I really want you to do is list all of the hex memory addresses that will hit in set 3. So you're going in the opposite direction now. Now you're given the tag. So set 3 is up here. I'll get my regular pointer back. Arrow. Excellent. So set 3 is right here. The only valid line in it has a tag of 32. So given that the tag is 32, the set is 3, find every single address that will hit. Basically these 4 addresses. So the reverse operation. I'll give you a couple minutes for that. Okay, so the tag is 32, so that's 0011, 0010. The set is 3, and because you're encoding the set with 3 bits, this is 011. And then the block offset, it could be any one of these. It could be 0001, 10, or 11. So this could be either 00, 01, 10, or 11. So if it's 00, then I'll put this XX, where XX you can substitute with any of these. So if it's 00, then what you have as an address is 1100, which is C. And then the next nibble is 0100, that's 4. And then the next nibble is 0110, which is 6. So that's the first address. And then you increment by 1, D, E, and F. Questions?
I like that one better, actually.
You'll probably get both.
It's going to take some
This is gonna be
repetition.
a long exam, isn't it?
Maybe. No longer than the other one was. Was the other one long? Ish. Okay.
Look at the practice for this one. It was like twice as.
You're right. It's not going to be that long. That was somebody asked for that, and it was my library of problems to give, and then I have to create a new library after I gave those out. So then, yeah, that really covers a huge breadth of the kinds of problems that I could come up with. So, yeah, and a lot of them are generated from the book. So,
How much, like, by memory assembly are we going to be?
you should know your modes for sure.
Yeah, most.
And then like the moves and the LEA quads, you should know those.
Do we have to remember like exactly what flags are set with the compare between two things?
No.
Okay.
I say no on that, but you should know some of the mnemonics like jump, JL being jump less than.
I can parse strings all day.
Parse
long,
strings, yeah, those are
remember
reasonable.
exactly
But
what
yeah.
flag
And like the
what.
Diana's silk dress costs.
Yeah, you should know that. Yeah,
Yeah,
that kind of stuff. Yeah. Okay, gonna skip this, and but you can go through it offline if you'd like.